The topic of climate change, its causes and consequences, is discussed by people all over the world. After a few introductory comments, I want to talk to you about how do we detect climate change, what changes the climate, how has the climate changed in history, and what are some of the effects of recent climate change, who or what is responsible, and what will happen next. It is important to understand that the climate has always changed. Whether we look at timescales of millions of years or thousands of years, the climate has always changed throughout history. If we look at the last 1000 years, we see that temperatures have been relatively constant throughout this time, except for the last approximately 100 years, where we see a tremendous increase. This dramatic increase of global air temperatures of somewhat less than 1 degree Celsius over the last 100 years or so is what concerns many people today. We use a variety of direct and indirect methods to arrive at the conclusion that our climate is indeed changing. Let's take a closer look at these methods. Today, it is easy to show that our climate is changing. We use thermometers to record temperatures. However, the thermometer was only invented in the year 1611 by Galileo, and the longest reliable temperature records in central England reach back to the year 1659. More comprehensive data were only available since the mid to late 1800s, when observation networks were established. And today we have a huge number of weather stations all over our planet. However, it is clear that we need to use other methods if we want to investigate climate change over centuries and millennia. One method that allows us to investigate climate change over millions of years is to investigate evidence from oceanic deposits. Researchers extract deep cores from ocean floors. The material contains bones and shells of plankton, which largely consist of calcium carbonate. The trick is to do an oxygen isotope analysis. In nature, we get two kinds of oxygen, which vary in their atomic weight. O16 is the most common form, O18 is the heavier, less common form. Water molecules that contain O16 make up 99.8% of water. This water evaporates more easily. Water that contains O18 makes up a fraction of a percent of all the water. However, it evaporates less easily. What does that mean for our global temperatures? During periods of low temperatures that do not facilitate evaporation, we experience expanding glaciers, and more O16 is bound in the glaciers. More O16 in the glaciers means less in the ocean water. As a result, we would see a higher O18 to O16 ratio in the ocean water or in the marine organisms. Analyzing oceanic sediments allows researchers to date back temperatures millions of years. Another method is to analyze ice cores that are obtained from Greenland or Antarctic ice shields and glaciers. Again, researchers use the oxygen isotope ratio to indirectly determine temperatures. It is based on the fact that snow that is deposited onto glaciers under warmer conditions contains more O18. Analyzing these ice cores provides even more information. You can analyze the gases that are contained in the air bubbles in the ice layers and thereby link temperature changes to changes in the composition of the atmosphere. Doing this yields a very interesting correlation between the concentration of greenhouse gases and air temperatures throughout history. We can get information about changes in the solar activity by analyzing the numbers of sunspots, which allows us to go back a couple of centuries. We can also analyze another isotope in rocks, beryllium-10, to get a better idea about solar activity going back thousands of years. We can use pollen diagrams to identify vegetation types that are linked to certain climates. This method also allows us to draw conclusions on the climate in a certain region at a certain time. Analyzing tree rings also provides information on temperature and moisture many hundreds of years ago. And finally, historical documents provide mostly indirect information on weather and climate. For example, they provide records of floods, droughts, or storms for thousands of years in China, Japan, or Egypt. Several factors can cause our climate to change. Let's look at them a bit more in detail. Our sun is a variable star, and the output of energy varies through time. It makes sense to assume that variations in solar output have an impact on the climate. Today, we have satellites that give accurate information on solar activity. But as we have learned before, we can use indirect methods to understand how the energy output of the sun has varied over hundreds and thousands of years. For example, analyzing sunspots leads us to the conclusion that the solar activity varies in rather distinct cycles of approximately 11 years. It is interesting to observe that we had periods with virtually no sunspots and others with up to 200. Linking solar activity to global temperatures allows for some interesting discussions. It certainly makes sense to link changes in the Earth's path around the Sun to climate change. These changes in the Earth's orbit are cyclical and are called Milankovitch cycles. We observe changes in the shape of the Earth's orbit around the Sun, called eccentricity. Variations in the angle between the Earth's axis and the Earth's orbit are referred to as obliquity, and precession refers to the wobbling of the Earth's axis. It is noteworthy that these Milankovitch cycles occur over thousands of years and cannot explain the recent climate change. It makes sense that changes in the locations of the continents, referred to as plate tectonics, will have an effect on the climate of certain regions. However, these changes occurred over millions of years and are also not useful to explain recent climate change. Atmospheric turbidity refers to the amount of suspended solid or liquid materials called aerosols. Changes in atmospheric turbidity can often be triggered by volcanic eruptions. However, volcanic eruptions typically have no long-term effects on climate. And finally, changes in the atmospheric composition or in radiation-absorbing gases should clearly have an effect on our climate as well. In particular, we're talking about greenhouse gases that are effective absorbers of long-wave outgoing radiation. The greenhouse effect has already been known for approximately 200 years. Without greenhouse effect, our mean global temperatures would be a lot colder. It is clear that an increase of greenhouse gases, for whatever reason, exerts a warming effect on the Earth's climate. So how has the climate changed in the past? If we look at the last couple of hundred thousands of years, we see 4 main glacial cycles, each lasting around 100,000 years. This is the time of the ice ages. The intermittent warm periods are called interglacials. We see that large parts of North America and Europe were covered by ice during the last ice age, which had its peak around 18,000 years ago. If we look for an explanation of these climate changes, then we find close linkages to the Milankovitch cycles. While the Milankovitch cycles are not enough to explain these tremendous temperature changes, it is very likely that they have triggered the changes, which were subsequently amplified by feedbacks. Here is an example for a positive feedback or self-amplification. Milankovitch cycles could have triggered an initial cooling. This cooling causes more of our planet to be covered by ice, which results in a higher albedo, which again results in more cooling. The climate change that concerns people worldwide refers to the change of global temperatures since approximately 1900. This change cannot be explained by any factor other than the greenhouse effect, and in particular the significant buildup of carbon dioxide in the atmosphere. That clearly begs the question, what has caused this buildup of carbon dioxide? It is evident that humans have emitted tremendous amounts of carbon dioxide since the Industrial Revolution in the late 1800s. And it would be impossible to explain the observed increase of carbon dioxide in the atmosphere without attributing it largely to these emissions. As a consequence, we have seen rising sea levels, shrinking glaciers, an increase of weather-related economic damages, an effect on ecosystems such as coral bleaching, the hottest years on record in the last decades, shrinking of the Arctic sea ice, an increase of heat waves or droughts, and many other devastating effects. While it is clear that our temperatures will keep increasing in the next decades, the magnitude of future warming will depend on the amount of greenhouse gases that we will emit in future.